All right. And let's go ahead and get that done. Okay. So let's see, where were we? We ended last time with let's see, selections for repetition structures. There we go. And as I mentioned before, we're skipping chapter 10, which is matrix operations and functions. For those of you who've had any kind of matrix algebra or linear algebra, you might find those chapters and those sections interesting. You can do MATLAB, of course, can do a lot with matrix mathematics since it's designed to do that. We're going to move into chapter 11, which is other kinds of arrays. And we're going to learn how to use arrays and matrices in ways that maybe we haven't thought that we could use them. And then we'll be done, should be done pretty early today, I think. And then we'll move on to, we'll skip chapter, so we're doing chapter 11, skipping chapter 10, going to chapter 11, we'll skip chapter 12. And next time we will skip chapter 12 and 13 actually and come back to chapter 14, I believe. Does that sound right? Yep, that sounds right. Okay, so chapter 11. Okay, so in previous chapters we built all kinds of arrays and vectors and matrices, different things that we've called them. The first thing we have to start off with, is a little review on the different ways that we can enter things into MATLAB, different types of data. And if you're on page, if you go to page 399 in your book, they talk about the different numeric data types. They also talk about data types that you can enter in, but numeric data types come in lots of different forms, starting with the double precision floating point number. This is something that is a standard number defined by engineering organizations and other things. They talk about that in the chat, in the paragraphs below there. But essentially, every one of these numbers, and this is the default for MATLAB. Every one of these numbers has some characteristics to it. Let's define a variable or an array of numbers. We'll just make it a very simple array, which is b equals 1 right here. And if we go here to our workspace over here, notice that it says it's a 1-by-1 double, 1-by-1 telling you the numbers of rows and columns. But then the double here is also something that's quite important. Also, let's see here. Here's our floating point double precision. Okay. Yep. So the double is going to is essentially going to use 64, what we call 64 bits of space. And what is a bit? Well, simply put, a bit is a logical yes or no, a one or a zero, an on or an off. If you go all the way down to the lowest level of machine language, the lowest level of programming language in a computer, what you're really doing is you're telling the computer to turn off or on a particular transistor in its electronics. Each one of those transistors is considered to hold one bit of storage, and that bit can either be off or on. Now, if you really like classic sci-fi movies relating to this particular subject, you need to go watch the original Tron movie, where the main character in the movie gains a pet called Bit, which can only say yes or no. And that is essentially the idea here. Is a bit only has two values: yes, no, on, off, 1, 0, positive, negative, however you want to call it. Two opposite things, values. And that is the basic idea of how computers work. That is the basic structure of a computer, are these many transistors that can either be on or off. And in the computer, it's either high voltage or low voltage in the computer. It's how it manifests itself inside the computer. And so people, computer scientists, computer programmers over the years had to figure out a way, a code of using these on-off bits to represent things like numbers and letters and colors and other things like this. The simplest thing to have them represent are numbers, because there is a binary number system that uses bits, that uses zeros and ones. And so you can use that binary number system to represent numbers. And if you have 64 of these bits, then you can store a huge range of numbers. And usually what happens is half of those bits are used to, so 32 of those bits are used to store a real part or a real portion of the number. The other 32 bits are used to store a imaginary part of that number, or a complex part of that number, so that you can actually do complex algebra or complex mathematics. But let's see. Okay, so you got those 64 bits for each number. 8 bits are considered a byte, and that has something to do with the way that the binary number system was organized to make numbers for computers. So every 8 bits that you use, you have a byte, and that means that each one of your numbers that uses 64 bits is actually using 8 bytes. Okay, so now we're kind of getting there. However, if we make a different array, let's make a different array now. Let's close this one out. Let's make the array, instead of b equals 1, we'll set b equals 1 to 10, like that. So now it's got 10 of these values in it. We can go here to b and open it up, and we notice that each one of these has, there's one of these in each little space here. Each one of these numbers now is going to be 64 bits or 8 bytes. And it's going to take 80 bytes to store this entire thing. Okay? And that's what that double is about. That double uses 64 bits. It uses 2 4-byte groups to store that thing, so that it's a double precision number. Now you can make a single precision number, which is single precision floating point numbers, and those use only 32, but you have to tell MATLAB to do it. So let's say we want to do that, and we want to make a single precision floating point number. We go d equals, this is on page, where is this, 401. And we're going to use the command single in MATLAB, and we're going to tell it that d is going to be a single precision, or we can also set MATLAB to be single precision. And the reason that you would do this is because you don't need as much precision. If you don't need the 64 bits allows you essentially to store more values, more significant figures in your number, or more decimal points, or whatever you want to say. But essentially just more significant figures. whereas the single only half as many. So if you don't need a high degree of precision, you can jump down to a single precision floating point number and use less computer memory and have a faster running program. In essence, if you have a lot of precision in your program, but not enough to justify double precision floating point numbers, and your program is extremely slow, you can speed up your program by almost double by switching to single precision. Well, not necessarily almost double, but you can speed it up quite a bit. So if we do this, then we go here to our D, and then we can see that it is a single precision floating point number. That means it's 5.000 out to a certain number of zeros and no further. And I can't remember how many it is, because each byte of numbers, I can't remember how precise a byte can be. It's not just 8 because there are 8 bits. The binary number system works differently than our number system, so it's slightly different. But anyway. You can format numbers in different ways like we've done before. You can do the short format, the rational format, the long format. Rational format gives you, fractions. Short format gives you 4 digits of precision. You can do the longer format. You can do a scientific format where it gives you, or engineering format. Either of those will give you times 10 to the stuff, the e to the stuff. And those are all just reviewed here in these next couple of pages. The important thing to know about those different types of numbers is that it uses, each one of them uses a different amount of memory and stores the number in a slightly different way. So they have different advantages depending on what you're trying to do. With the kind of programming that you're doing, not necessarily important that you pick one or the other kind of format. But as you're doing more and more complex kinds of programming, if you become a programmer of some kind, then you would definitely want to know that those are available to you. Also, there's this, you can also do integers, and I mentioned complex numbers in the very next section. We talk about complex numbers and how you would put it, how MATLAB is able to use complex numbers. We are not going to do anything with complex numbers. For those of you who do not know what a complex number is, a complex number is a number that has a real portion and an imaginary portion. The imaginary portion usually coming from some square root of a negative number somewhere. And so MATLAB can deal with that. MATLAB can keep track of those things, can do mathematics with those kinds of things, and not have any problem. Now, getting to section 11.3, which is where we really want to get through for this class. And that is character and string data. So just like numbers are stored in a certain number of bits or bytes, characters are as well, characters and strings. What a character is an individual letter or an individual character like on the keyboard. If you put into MATLAB, if you put in 5 times 8, for example, MATLAB does not treat that little star as a character. It treats it as an operator. MATLAB knows that when you type in the star, that you really mean multiply. And so there is a program that is associated with that star, not a character. If you want the character star, you have to put it into quotes. G equals star. Put that into quotes. And then MATLAB recognizes it as a character. And those two things are different things. Okay? Whenever you see a character or a string in MATLAB, it will just show up as its character in the array or in the whatever, in the character array. If you look in your workspace, it will show up with quotes around it so that you know that it's a character or a string. A string is just a list of different characters one after the other. So if instead of doing G equals star, I do G equals star space, I do G equals star space shift underscore H 5% $sign exclamation point or something like that. MATLAB recognizes each one of those things as a character, including the space, when you put it inside of quotes. And it can even recognize things like tabs as characters. And for each one of these characters, there is a code that is encoded into MATLAB that takes up a certain number of ones and zeros or offs and ons in the bits and the bytes of the computer. And it uses a code that is called ASCII code, just like most computers programs use. ASCII code is a code that assigns each character a certain value in the binary number, like a code number, and then essentially when you want to type in these numbers, it stores it as that number, because computers don't really store characters or words or anything like that. Computers only store numbers. And so there's a particular code that tells the computer this next thing is going to be a string. It's essentially a particular number. And then there are particular numbers that are used to denote different characters that you might want to type out in a particular string. So this is a string of characters. This is a single character up here. So that is some of the language that we use when we're talking about characters and strings. There's another way to tell MATLAB that you're using a string, that you want something to be a string. And you can do that by saying, A equals, and then using the string command and putting your string inside of parentheses here. In the case of using the string command, you do not need to put quotes around your stuff inside of the string command. So I might just say Jared is my name, like this. And it recognizes every single thing in here as a string except for the exclamation point, apparently. No, it doesn't want to do that. Apparently you do have to put it in single quotes in here. Let's try that again. Oh, so string is obsolete, and it's in this new book. That's no good. So we're going to use the thing character instead. So we're going to use character, CR, char, and then hit enter. And it stores Jared is my name as a string of characters in A. And you can see up here, you've got the string of characters that are up here. And if you count all these things, we've got 1, 2, 3, 4, 5 in my name, 1, 2 here in is, 1, 2 here, that's a total of 9, and then 1, 2, 3, 4 over here, so that's a total of 13. We've got a total of 13 letters, but then we have 3 spaces, which are also considered characters. So it's a 1 by 16. Okay, now, just like with other arrays, you can manipulate these arrays and do things with these arrays just like you would with other arrays. For example, this array A, which says Jared is my name, has a certain number of elements, and I can pick out any element I want by picking out the number of the element. What is the 5th element in that array? The 5th element is the character D. Pretty simple, right? I can also do A 5 through, no, let's do 1 through 5. And it takes out the first 5 from the array, Jared, right? You can also make another array. We could say B equals character, and I'll do and don't wear it out, right? It doesn't like this because that's a single quote. So when you do a single quote here, you have to do a let's see, you have to do a backslash. No, that's not right. Let me see if I remember how to do this. Well, we'll figure it out here in a second. So I can do this, and B is now going to be don't wear it out, and I can also do, and I can do something like create a new array of A comma B. Oops. A comma B. There we go. But then there's not a space in there, so then I got to put a space in there, of course, right? A comma quote space quote comma B. Jared is my name, and don't wear it. Okay. So anyway, you can do things. You can do just the same kind of things that you were able to do with matrices that you were able to do with these things. We could also put these in separate rows, right? Oops. Oh, so I couldn't do this one because A is 16, is 1 by 16, and B is 1 by 20. So I have to change A into something that's more than 1 by 16. It needs to be 1 by 20. They need to agree in their number of columns. So I could do that, I suppose. Let's go up to A and let's edit A. Jared is my name. And I'm just going to put 1, 2, 3, 4 spaces at the end of it. And then I'm going to save that. I'm going to close that and save it. So now it's a 1 by 20. Now I can do a semicolon B. So now you can put them together. So pretty simple stuff. Let's see here. What else can I do here? So we can also combine arrays that have numerical things and string elements and numerical elements. So for example, if I have A, which is 20 numbers, and then I put in the array 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 15, 16, 17, 18, 19, 20. Well, it didn't like that. So let's set C equal 1 to 20. And let's do AC. Oops, yes, I did mean that. Why doesn't it want to do that? Well, because it probably didn't do it right. Oh, yes, I didn't do it right. So, excuse me. Let's do it the way they do it in the book because it's simpler and fewer things that go wrong. So in the book, we're going to create two simple variables here. We're going to create the variable A. Let's see, I'm getting ahead of myself here. Oh, yes, I definitely got ahead of myself because I forgot to mention I forgot to keep going with the ASCII code thing. So anyway, ASCII code is described at the top of page 406 for character encoding strategies. I kind of skipped this section. And the ASCII, let's see. Okay. So if we do this, if we use this command, the double command, with a character inside of it, what MATLAB wants to do, what MATLAB is going to do is it's going to give you a double precision floating point number that is associated with the character A. And it happens to be the number 97. So this is not the binary code number associated with A, but when you take that binary number and turn it into just a regular number, it gives you 97. So the lowercase a is 97. Uppercase A is actually a different one. Should be anyway. Yep. Uppercase A is 65. And you might think that they're in order, so you look at lowercase b and let's see what happens. They are in order. The lowercases start at 97 and then go up, and the uppercases are also in order, going from 65 and up, right? So that gives you a representation, excuse me, a representative number for each character that there is in MATLAB, and it works for any character you can type on the keyboard. Even the space character is the ASCII number 32. The tab. You can go through and look at all these things. The tab. Oops. It doesn't want to find. It won't let me put the tab in there. The tab is its own little thing which you have to figure out how to do, which we'll learn later. Let's do this one. Let's do the greater than symbol. And then do that one. That one turns out to be 62. So each one of the characters on your keyboard has an ASCII number, excuse me, associated with it. Now, if we do the character, if we go back to the character command, it will actually do the opposite thing for numbers. So if you put in the 98 again, for character, it'll tell you which character is associated with 98, which is the little b. And if you put two different things into an array, you put the character A and the number 98 in there, it will actually convert the 98 into a character. So the answer is AB, because the first thing that you put in was a character and the second thing was a number. Now let's see if it does the exact opposite. I don't know if it will. Let's see if it does the exact opposite if we put a number in first and then we put in a character second. Maybe it will do it. Maybe it'll change them both into numbers. I don't know. No, it doesn't. Just do characters. So if you have characters in the matrix at all, it just changes them into characters. Oh, excuse me. Okay, so it turns out that not all the numbers have a character equivalent. So if you put in 1 with A, it leaves it blank because there is no character associated with 1. The numbers 1 through 9 and 0 also do not have characters associated to them because they're used as numbers in the decimal system that we use. So they do not have a character associated with them. They're just numbers. Okay, so what else here? That's about it, I guess. All right, so let's do some more things with, let's learn some more things that we can do with character and string arrays. 11.3.3, page 407. Again, you will notice that a lot of these things we can do with, we're doing with other arrays, normal arrays, numerical arrays all the time anyway, so it's not really that big a deal. Let's go ahead and do them anyway. we're going to say we're going to build this array of strings. So our first string is going to be Stephen. And then our second string on the, we're going to put on another, we're going to put in a new row. We're going to put in Megan. Then a new row, we'll put in David. I always forget my first quote. And then in a new row, we're going to put in Michael. Now I pushed the wrong number, the wrong thing here. There we go. And then our last one is Heidi. So what that, oh. Let's see, what did we do wrong? Oh yeah, that's what we're supposed to do. Okay. So let's see what we did wrong. It's actually fairly easy to see what we did wrong. Each one of these things is considered its own special column. So Stephen is a column, and then a new row, and then Megan is a column, and then a new row, and David is a column, and a new row, and so on and so forth. But they're all not the same length. Stephen has 6 in it, Megan has 6 in it, David has 5 in it, Michael has 7 in it, and Heidi has 5 in it. So this one needs an extra one. And if we add a space here, it should work. Megan needs an extra one to be 7, Stephen needs an extra one to be 7, David needs an extra 2 to be 7. Michael is 7, and then Heidi needs an extra 2 to be 7. If we do this, we should be okay. Let's see what it gives us. Yep. So each one of these is a, well, sorry, each one of these is a row, and each one is it's an own row, and Stephen has 7 columns, with one of them being a space. Megan has 7 columns, one of them being a space. David has 7 columns, with 2 of them being a space, and so on and so forth. So, was there a question? Sorry? No question? Okay. Anyway, we've done this kind of thing before, but we didn't really have this problem with trying to figure out how many things we needed in each row, because it made sense to have the same number of things in each row. In this case, each letter is considered its own column in this row, and if you don't have the same number of letters in each name, you have to add some on. You can also use the character function to do this. So if I do character, and then I put in this same array that I started with, copy this one. So I should do character 1 actually. And then I paste in this same array, which doesn't have the extra spaces in it, which gave me the error before. It's because I'm doing it wrong. So I'm going to call this, oh, I called it M before, not character 1. Let's call this N this time. And then we're going to use the function character, which is what I was trying to do. Okay. What am I doing wrong? I'm obviously doing something wrong. Oh, yes, I'm doing something wrong. I need to have parentheses around this now because it's a function. So I put my parentheses around it. I had the square brackets around it because I was just defining it as a function before. This time I'm actually going to define n to be this array of things that I put inside of the character function. And it's still not going to do it because it's expecting commas, not, goodness, I'm just messing this up left and right. I have to change everything. I can't just copy it over. All these have to be commas. You put commas in between the individual strings in functions generally, or in between individual arguments you put in commas, which I didn't have. Now it should work. There we go. And so what this did is it created these extra spaces already in these ones. If we look at the two things that I've done here, M and N, both of them are 5 by 7 because that's 7 being the number of columns, in the first one, in M, I added the extra columns in by hand by adding extra spaces into each name. In the second one, the computer did it for me, which of course is much faster. So you have these two functions that we've used so far, the character function, char, and that thing, the character one, does things to character strings. It can change character string, it can find the character for a particular ASCII code, it can balance character arrays and so on and so forth. And then the other one is the, what's the other one called again? The other one is called the double function, which will, if you type a string into it, it will give you the double precision ASCII code number for your string that you type into it. So anyway, what are some other things we can do here? So another function that is used quite often is the string function. This one you can do the same. You can do the same thing that we just did, except to use the string function. You actually have to type it in as an array. So we do string here, and then inside of the string function we type it in as an array. And when you put an array inside of a function, you don't use square brackets. You use the curly brackets. So we put in the curly brackets, and then in between each of these, we do need to go back to our semicolon, because now it's an array again that we're defining. And then we close it off with one of these little curly Q things. I have no idea what those are called. And that will do the same thing as before, or at least it should have. Oh, the string one is obsolete. So we can't use it anymore. So we're going to use the character one instead. So apparently there's a lot of stuff that's gone out of vogue. And that's fine, I guess. Another thing that you can do is you can actually create strings out of numbers. So MATLAB, when you type in 8, it treats that like the number 8. In other words, it's not thinking it's a character at all. It's thinking it's the number 8. And to the computer, that means something different. The number 8 in binary numbers, for example, is not 8 as we see it here at all. It's a binary code. In the binary code, your first digit is your last digit is your 2's digit. Your second to last digit is your 4's digit, and then your 8's digit, and so on. And so you would have a 100 for 8, essentially. And depending on how you want to do it, you can do it the other one as well. You can do 001 for 8. So it treats it as that binary number in MATLAB. It knows what it is, and it can treat it as such. But you can actually you can force MATLAB to treat a number like a string. And the advantage to doing that is then you can start to mix numbers and letters more easily, because the numbers are now strings. So how do you do that? You do that by doing using this one here called num2string. This is another, is it num2string or numstring? No, num2string. Num2string, right there. So this is a function that converts a number into a string. So let's see, where was I here? So let's just do a number 90, for example. Goodness gracious. So it says the answer is 90, but if you go over to your workspace and you open it up, you'll notice 90 is in there, but this is now a 1x2 character array. This is not a 1x2 double precision number array. It's a 1x2 character array. And if you look here in your workspace, it's got quotes around it. So now MATLAB is treating it as a number. And if we make an assignment like this, we go A is equal to num to string 90. So now we've stored 90 into A equals 90. And I do A plus 5, right? It has no idea what you're talking about. You just did A plus 5 where A is 90 and it gave you 63 and 62 and 53. What the heck is that? Right? Because it's a string. It's not a number, it's a string. And if you go back here, you notice that it's a 1x2 character array, which means it's got two characters, a 9 and a 0 in it. Right? And those 9s and 0s, when they are strings, are represented differently. So you can't just, well, 90 when it's a string is represented differently, I guess. So you can't just assume. So if we go, let's go to back to our function. Let's do character 90. No, that's not it. Let's do double of 90, 57, 48. Yeah, so that's what we did right there. So if you look for the ASCII code for 90, it gives you the two numbers, 57 and 48. When I added 90 as a string, added 5 to 90 as a string, what it did is it took the two numbers that represent the number 90 as a string, and it added 5 to each of them. Right? And you got 62, 53, because that's 5 plus 57 and 5 plus 48. So it doesn't make sense to start adding things to strings, but if you define A as 90 as a string, then you can put it together with other strings and make sentences and things like this. So this has uses for sure, but they're not mathematical uses necessarily. So here's one of the ways that you can use these tools, and that is to manipulate the names of files that the computer has stored. You can manipulate those names of files through MATLAB. And that can be extremely useful because you can create a file in MATLAB, then you can store data to a file in MATLAB, and then you can name that file in MATLAB. So you can have MATLAB taking data on a particular day and then storing it in a file and naming that file with the date and the time that it took it. All as strings, because the names of files on your computers are strings. So you need to be able to name them as strings. So let's look at an example of this. Here they do a thing of code here where they're storing some data on a file. The first thing that they do, if you see, so they've got a file called some data, and I don't know, I'm pretty sure that's not included in MATLAB. Let's try it out anyway, though. Yeah, some data is not there, so we're not going to be able to load it. But let's say we were going to load a thing of data. Let's look. I've got this data. I've got this file here that's AB. What's AB? No, let's load. Let's try to load some other file that I might have here. Sure, why not? Let's load this one. So we're going to load Mimas underscored Cassini. So now MATLAB has that data stored into it. It's got that sitting there somewhere. It's right here. Mimas Cassini. It's an 1800 by 1800, and the type of file that is they call it, what do they call this? Unitary 8. So it's a different kind of data, but it is some data. We've loaded that data in, and now I want to see how big this is without just looking over here. So since I'm not looking over there now, I'm going to say I'm going to load the rows and columns into a matrix. The number of rows and columns, rows, comma calls, right, and that is going to equal the size of my thing that I just loaded in here, which is Mimas Cassini. So the rows are 1800, the columns are 1800, just like I expected. And then we're going to use a for loop here. So we're going to use k as our index. K equals 1 to number of calls, right? And I'm going to do a file. I'm going to do a file name. Underscore file name is going to equal and I'm going to use a string. My file, my data. They say my data here. And then I'm going to use num to string, which was character for k. They used character instead, right? No. I think they, well, anyway. So what it's going to do is it's going to take the number k that we're stepping through here, and it's going to actually put that into the file name. Oops. So it's going to be my data 1 for the first time through, or my data 2 the second time through, my data 3 the third time through, and so on and so forth. And then data will equal sum. It's going to equal Mimas Cassini. Control paste. Mimas Cassini. And we're going to take everything in the first row, first column, every row. Okay, and then we're going to save it. So we're going to save to Mimas Cassini. And we're going to put data in there. So what is this actually going to do? It's going to go around. It's going to go around 1,800 times, starting at 1, and then 2, and then 3, and then 4, and then 5, and it's going to store each one of the columns. Because right here we're taking all the rows, first column. So it's going to take the first column, all the rows, right? So we're going to look at. We're going to take one column at a time and save it to this new file called my data 1, and then my data 2, and then my data 3 each time we go through each column. And let's see what happens. Arguments must contain a string in save. Something went wrong in my for loop. So let's try again. I probably shouldn't have printed it out, because that's a lot of things to print out. So it went through, it looks like, one time. And let's not print out this right here. Well, let's go back and copy all this first. So on the last one where I put in the save, I needed to put in What did I need to do here? Oh, it's not. I don't want to put, I did that wrong, I see. So let's copy this, put it all the way down here again. And we'll paste. So I need to put file name here. There we go. And then let's try it now, but let's not print out everything because that's kind of crazy. And then let's run it again. Ah! I put it in a folder instead of a file. Let's call it, ooh. That should work. Why isn't it working? I think because my data is already taken somewhere. So let's call it put it there. That should work. Let's suppress this and this. Suppress everything. Let's try it again. Ah! Why does it, oh! It's thinking it's a, I didn't put it as a folder though. Why is it doing that? That should work. Got to do a little debugging here. Okay, let's try. Let's go back to here. Okay, now it did it. It just didn't want the, it didn't like the character version of it. Okay, so now I've created a whole bunch of data files here. JED data 1, 2, 3, all the way through. Notice how quickly it does 1,800 of these files. So it created a whole bunch of these files, and the great thing here is if I open up one of these files now, which I should be able to open. It's 1800 by 1 and it has all the data in it. I want to see the data. Let's see. Right here. There it is. So here's the data, and it turns out that this particular column is mostly zeros, and that means that it's I think 0 is a white pixel or a black pixel, one of the two, I can't remember which. So, because I think it's a black, I think the Cassini picture is a, oh crap. I just closed MATLAB. I think the Cassini data file is just a bunch of pixels. But I think it does have colors in it, so I think that I think that 0 is white or black, and then other colors are different numbers. in your data file. But anyway, this can be very useful to you if you're taking data, and MATLAB is used for this a lot, to take data periodically and then store data into files that are actually named. So that particular little for loop there is used quite a lot. And it's not always a for loop. Sometimes it's a while loop. Sometimes it's an if loop. You know, if this certain thing happens, you know, store some data or take some data or whatever, and then store it in a file. But to do that, you have to be able to name the file using a string. You can't name the file just using, you know, typing a name in MATLAB. If you type the name U in MATLAB, and it assumes that U is just a variable name, right? And now U is a number, and you can add to it, right? So it just assumes it's a variable name, does not assume it's a string, but you can deal with strings in MATLAB. You just have to make sure that you do it the right way. Okay, so moving on to the next section. Oh, here in example 11.1, they do a secret code where they're going to assign letters or words or strings essentially to numbers, right? And then they create a case switch loop where if you put in certain numbers, you get out certain words and things like this, right? And you're welcome to do that if you want, but it's not that big a deal. Okay, so far we've learned that you can store numerical data in several different ways in MATLAB, and then you can store strings and characters in MATLAB in a couple of different ways. In 11.4, they tell us that we can store symbolic data, which is essentially algebra, but you have to use the symbolic toolbox for that, so we're not going to go through it. It's only a very short section anyway. But then the next one is logical data. So logical data is, of course, true, false, yes, no, 1, 0, essentially. And MATLAB easily does this. Excuse me. Excuse me. And when you're entering in arrays in MATLAB, we usually don't make arrays that are logical, but we often receive arrays that are logical from MATLAB. So, for example, if you have two arrays of numbers and then you ask if one array is less than the other array, and they're the same size arrays, then it will go term by term through the arrays and check to see if one of them is less than the other one, or greater than the other one, or whatever it is. And so it looks like this. If we do x equals 1 to 5, this is on the bottom of page 413, by the way. And y is equal to 20194. 20194. And then we go ahead and ask MATLAB. We're going to say z is equal to x greater than y. So we're setting this logical array. Now we could do this just x greater than y. We could just do this. Is x greater than y? And that's the question we're asking them to do that. And the answer it gives is term by term. It goes term by term through it and it says, the first one, is the first one of x greater than y? No. 0 is no. Is the second one greater than y? 2 is an x. Is the second one an x? 0 is the second one of y? Yes. Is 3 greater than 1? Yes. Is 4 greater than 9? No. Is 5 greater than 4? Yes. So is a no, yes, yes, no, yes. Or 0, 1, 1, 0, 1. You could also ask it to set it equal to a particular array and put those numbers in an array called z, and then you have an array called z, which is a logical array, and then you can use that array to do other things. Ugh, excuse me. So that's logical arrays. Sparse arrays. Okay. So a lot of times when you're dealing with, sorry, my head's hurting a little bit. A lot of times when you're dealing with arrays, many of the elements of the array are zero. They're just placeholders in the array. And one way to store an array like that is to use the sparse command. And in the sparse command, what the MATLAB does is it remembers where the zeros are, but it throws out the data in that part of the array, and it makes a much, much smaller array of the actual numbers that need to be remembered. And in doing that, you can save a lot of memory space. So the example that they give is a 1000 by 1000 identity matrix. The way that you do that, an identity matrix is a matrix that has a 1 along the diagonal and zeros everywhere else. So U is equal to I, and we want to do 1000 by 1000 matrix. We put 1000 in here, and that'll make an array of 1,000,000. It'll have 1,000,000 things in it, 1,000,000 elements, 1,000 rows, 1,000 columns, and this is what it looks like. One's all along the diagonal here, from the top left corner all the way down to the bottom right corner, but everywhere else is zeros. This array takes up a huge amount of space on the computer. So it takes up 8 megabytes of space to do this. Each one of those numbers taking up 8 bits, rather, 8 bytes. And then it takes, there's 1,000,000 of those numbers, so it's 8 megabytes to take that up. Now, to give you an idea of how much that is, that's equivalent to a fair-sized picture, like a fair-sized photograph. And it's just an array of zeros and ones. It's nothing that big a deal. If we use the sparse command to make a sparse array of this, we say that V is capital V they're using, that's fine, equals sparse command, just use sparse, and then we put in U into there. It takes up a lot less space. So the 1000 by 1000 sparse double array ends up taking, it takes up 24 kilobytes, 24,000 bytes. So 24 kilobytes is less than 1/40th of the space that the original array took up. So it's a lot less. Let's see, it's 25 kilobytes, 8 megabytes, 1/4 would be 1/40th. Yeah, takes about 1/40. It's a little bit more than 1/40th of the original thing. So quite a bit less, anyway. I think it's actually even less. It's 1/400th. It's 1/400th. It's a really small amount. It's much smaller for storing. The only time that it would change the array back into its original array is when it actually had to do mathematics with the array. When it has to do mathematics with the array, it would switch it back into its normal size, do the mathematics, and then go back to the sparse array. Categorical arrays. So categorical arrays are often, we often call them cell arrays, and they are a cell array. And what that means essentially is that instead of creating an array of all the same kind of things and just throwing them as an array, like all strings or all numbers or whatever else, we're splitting each element of our array into what we call a cell, and then each one of those cells can be treated kind of like a different array. So this is where we're starting to get into higher than two-dimensional array kind of things. So this gets to be a little more complicated. So let's take a look at what we're going to do here. In this particular case, we're going to do a time array. In this particular example, we're going to store a date and a time using standard date and time kind of entries. And then we're going to do some math with those things. We're gonna actually manipulate those things doing some math. So we'll start off with developing some arrays for years, months, and days. So a year array will be an array of numbers from 1990 to 26. No, actually, they're just doing two different numbers. So 1990 and 2016. So we've got two numbers in that array. And then we've got our month array, which will equal 2, 5. And we'll have our day array, which will equal 1, 20. And each one of these should actually be arrays, not row matrices, but column matrices. The only one that I did correct is actually the last one, the day one. Did I do that right? There we go. Day is 120. So that one I did correct. So I got to redo year. Let's make year equal to year, and we'll make it into a column array. Do the same thing with day equals day column. Okay. Oops. No, day was right. Day equals day. It was year that wasn't right. We did year. Now we have to do month is not right. Month equals month. Turn it into columns. Okay, now we've got it. So now day, year, and month are all column arrays, and that's great. Next thing we want to do is we're going to create this array where we have x equals date, time, and we're going to do year, comma, month, comma, day. So date time is a function that MATLAB has that will turn years, months, and days in numbers into the correct format that we're used to using. This is maybe not the correct format we use in the United States. This particular format is more like the format they use in Europe, but it's still a good format. But then we can also do, we could also take differences now. We could take the differences in months and the difference in years, the difference in times, add months, add days, add times, and then create a new day, month, and year for a later time or an earlier time. So, I mean, immediately you can do all kinds of things with that. You can also do it with time. Do the same thing with, let's see here. I believe you can do the same thing with time. Let's check that really quick. Let's do help, date, time. So calendar days, months, time difference in hours, minutes, seconds. Yeah. So you can do so in date time. In date time, it looks like we do years, followed by months, followed by days, followed by hours, followed by minutes, followed by seconds. So the numbers after here can also be minutes and seconds. So let's do that really quick. Let's do hours equals, let's give ourselves 2 hours. I'm going to assume that it's going to go from 1 to 24, so let's do 3 and 15. That needs to be in columns again. And then minutes, we'll do 45 minutes, and we'll do 12 minutes. And then seconds, we'll do 54 and 22. So now we're going to do this. Date time will now be year, month, day, hour. It's hours, minutes, seconds. And it sets it up that way too. It sets up with the hours, minutes, and seconds. So you can do both of these things. And then of course you can see that numbers now can become dates, times, and everything. And then you can actually take the date and time from the computer using this function as well. So if we do a date, time, let's see, I think if you just write in date time, yeah. So date time tells you the date and the time right now. And if I do date, time, and I can actually put in, I think I can put in tomorrow. Nope. What can I do? Well, anyway, inside of your program, you can put in date, time, and those things get put into an array. So if I do today in class, for example, equals date time, then today class becomes this thing that shows up on your screen here. But if I look at today class in here, it gives me, it will actually store those as numbers. Right now it's stored as a date time value. But if I look at the actual numbers of date time by using string to num of today class, it should give me some numbers. No, it doesn't like that. Character. Today class. I probably have to do the double. So I'll do double of today class. Nope. First, we're trying to daytime order to convert to using second sentence use functions. Oh, those have functions. Okay, so I actually assigned a value to seconds, minutes. Okay, so if I want to know seconds of date time of today class, there is a function called seconds. Help seconds. Yeah. Let's see here. For the years, today class. I'm not sure how to switch that to numeric. Let's try. Oh, there it is. So if I use the function double today class, it gives me all the ASCII codes, or all the ASCII codes that are being used to represent the years and the dates, the years and the days and the months and the times that are in here. And then I can start doing things with those if I want to. So anyway, just different ways that you can store. There's lots of different ways that you can store different kinds of things in arrays. Let's see. 11.9 multi-dimensional arrays. Now, it's hard to visualize what a multi-dimensional array, what a more than three-dimensional array would be. But essentially what it is MATLAB can deal with this. MATLAB doesn't care if each cell is split into two different other things. But so when we start off with a single thing, so y equals 2, 3, 4, 5, whatever, we create, y equals 3, 4, 5, 6 in an array, so we put it in array format, and it just assigns them into these separate columns in one single row. And then if we put in another row of these things, each has a row and a column. MATLAB doesn't care if each one of these rows and columns has something else that we call, we have a row, a column, and then each one of those row columns has something else we call a bottle, and it's full of things. So it's like putting a can or a file in each element, and each one of those files now has 20 files in it, or 50 files in it, or something. And MATLAB wouldn't even care if each one of those files that's in that file cabinet is a file folder with 50 documents. And each of those documents had an array in it that has rows and columns again. MATLAB doesn't care. It just needs you to tell you that. It needs to know that. And so you can use, there's a particular function, or there's a particular way of doing this, I guess is the best way to say this. Let's see. Okay, so they defined them. Let's go ahead and clear and start over here. And let's say that we're going to start with this one. X equals, so we're going to do the one that they do, 1, 2, 3, 4, 5, 6. That's fine. 1, 2, 3, 4, 5, 6. So there's our first thing. It's our, this row, and then we're going to say that y is going to equal 10 times x. Simple enough. And then we're going to say z equals 10 times y. And then we're going to define w as well to equal 10 times z. Just fine. Do that. So that's all easy stuff that we've done before. We have an x, we have a y, we have a z. Oops, that last one was supposed to be not x. That was supposed to be w. Then I have to redefine x. So let me redefine x really quick. So now I have an x, a y, a z, and a w. All of them 1x6 two-dimensional arrays. Now we're going to put pages onto these arrays, they're going to call them. So let's see here. How we can do. So we're going to do this by using our colon notation. And if you remember our colon notation, we used a colon to denote an entire row or an entire column, and then we put particular things in the other place. So it's going to look something like this. We're going to use this my underscore 3D array. You can call it whatever you want. They're just calling it my 3D array. And then they're going to do first row, first column, and then they're going to define the first page. So this is every row, every column, every row, every column, and they're going to define a page. They're calling it a page. It could be a file, a cabinet, it could be whatever you want to call it. But they're calling it a page, and they're calling it page 1. And in page 1, we're going to put X there. So X is going to go into this particular place. It equals X. In that particular place in my 3D array. Okay? So now I'm going to go ahead and hit return and see what happens. So my 3D array looks like X. 1, 2, 3, 4, 5, 6. No big deal. Then I'm going to do the same thing again, and instead of doing it in the first page, I'm going to put it in the second page, and I'm going to call that Y. Okay? So now my 3D array has two things going into it in these pages. This one in the first page, this one in the second page. 10 times that next one. And then I keep doing that. I do that with the next one. My 3D array, page 3, is going to be Z. And then my 3D array 4 is going to be W. Right? And you can see this is just getting bigger and bigger and bigger. And then, what happens when I just call it my 3D array? What is my 3D array going to look like? My 3D array is going to be difficult to really describe on a two-dimensional screen. But what they're showing you here is that in all the first rows and all the first columns and the first page, we have this thing, right? And then in all the first rows and all the first columns at the second page, we have this thing. And what that means is that this thing has been repeated 6 times. No, 4 times. No, let's see. Yeah, this has been repeated several times, in other words. So there's a lot more than just 4 things going on here. These things are in many different places in this array. And you can keep going with this. You can go on and on and on. You can keep adding to your array using this this kind of code, this colon codes. Anyway. They have a nice way of visualizing it here on page 421, where you have rows and columns, and then you have pages moving back away from that, and that's fine. You can think of it any way you want, but that works as well. All right, we're getting close to the end of this chapter. We have, I think, 2 more sections. Yeah, 2 more sections. 3 more sections, actually. And these next 3 sections are the way to think of these next 3 sections are kind of with kind of going back to the arrays of strings, you could think of them as, or even the arrays of pages. We're going to be doing arrays within arrays within arrays, things like that. So the first one is called the cell array, cell arrays. Okay, so what is a cell array? A cell array allows you to create within each element of each array its own little box again, very similar to the multidimensional arrays, very similar to other things we've done. But inside this box now, you can put pretty much anything you want. You could put another array of a different size, a vector of vectors of different sizes. These cells are designed to be kind of like little lockers that you put whatever you want in them. And cell arrays, they have to be set up a particular way, but it's not all that hard. So let's go ahead and do one. Let's just get started with doing one. All right. Hello.
Hello.
Sorry, I'm teaching distance learning right now. Okay, so let's start off with simple array. A equals 1 to 3. Just a very simple thing. And then we'll do B, something a little bit more mysterious. We'll do a string array, an array of some strings, just put in some letters, whatever we want to put in. Simple enough. And then we're going to put in the last one. We're going to put in a single, for our last one, we'll put in a single precision array. And this one is going to be just 1, 2, 3, 4, 5, 6, I guess. So that's fine. Single 1, 2, 3, 4, 5, 6. Great. So each one of these is quite different. They're different in size. They're different in type. They're just very different. And you can see that they're different over here. A 1 by 3, a 1 by 13, a 1 by 6. Quite different. Now we're going to go ahead and create a cell array. We'll just call it array. They call it my cell array. Don't have to call it anything. Doesn't have to have cell in the title. Just call it whatever you want to. And I'm going to create this array using, instead of square brackets, I'm going to use curly brackets. Oops. Curly brackets allows us to do this. So we're going to do A, comma, B, comma, C. Okay. And this is now a cell array where each one of the elements in the array is its own little thing. There's a 1 by 3 double, there's this string array, and then there's a 1 by 6 single. And over here it is stored as such. It's stored each array separately, so it's very similar to a multi-dimensional array, and you can make them as big as you want. You can make the arrays within the arrays as big as you want as well. So within the array you could have a multi-dimensional array inside the cell array. Or you could have a 2 by 6 or an 8 by 8 or a million by million, whatever you want. And it can be an array of strings, an array of string arrays. You can have, you can have cell arrays within cell arrays. You can have all kinds of things going on. And this, of course, has incredible usefulness. You can store all kinds of different things inside of a cell array and then call them by you calling this thing. So array. So if I want to call array, let's call array, array 2, it calls that middle thing, right? And if that middle thing, instead of being H, J, D, S, K, L, whatever it was, instead of that being that, it was please press start, then all of a sudden I've created now this array of commands that I can go to, these string commands. Or maybe it's a number that I'm going to use in a particular situation, or an array of numbers, or an array of whatever. It could be an image. You could store an image in here as an array of numbers so that you could call up different images. If you wanted to create a deck of cards, you could create a deck. You could create an array of 52 different images, right? And then you just call it the 52nd card or whatever. Maybe that's the ace of spades. So these things have extreme usefulness, a lot of usefulness that is really infinitely variable. You can do infinite number of things with cell arrays. Let's see, what other things do they talk about with cell arrays? Yeah, okay, so cell plot is something we can do here. This kind of tells you the, it's going to give us some idea of what's going on in the cell array. So it gives us this graphical representation where we have these three things going on in the first part of it, right? The three things which are the numbers, the three numbers. They started within this string in the middle, and the colors represent different things, single, double, string. So it gives you an idea of the structure of that array. All right, and then the second to last section, we talk about structure arrays. One more different kind of array. So structure arrays are also like cell arrays in that they store different kinds of things in them in different cells. However, in the cell arrays, I would call up array 1 or array 2, and we would have this indexing. So this one is the first one, this one's the second one, this is the third one. And that's how it's done in a cell array. That's how it's indexed. That's how it knows how to keep track of things in a cell array. In a structure array, it's a little bit different. In a structure array, you assign locations to things called a field. And let's go ahead and show you kind of what this looks like. With our array that we used before, array that has ABC in it, I can do array 1, for example. And it pulls up the very first thing in there, right? It tells me what it is anyway. And then if I pull up array 2, it shows me the string, and array 3 would show me this 1x6 double at the end here. However, in the structure array, we put it together differently. So if I want to do a structure array, I'll call it structure. Structure. Let's see if that's used. Okay, so structure is not used, so I can use it, and that's fine. I'm going to use it. So my array is going to be called structure array, and I'm going to set it equal to I'm going to give it now a handle or a what do they call it again? They call it a field. So this is all in other programming languages sometimes called a handle, but here we're going to call it the field. So I'm going to call it some numbers they use, and that's fine. That works just fine. And then I'm going to set that equal to A. So structure dot sum numbers equals A. The structure is the name of the array. The sum numbers is the label that I've given to that particular field in the array, and that's A. Right? And then I do the same thing again. Structure, instead of some numbers, I maybe put in some letters. And that's going to be B. And I plug into that. And then I do the same thing again. Instead of some letters, I put in some small numbers. Or something like that. And I'll let that equal C. Now structure is going to store these things underneath those values, underneath those names essentially. So I could go ahead now and I could pull out some letters or some structure out of structure, some numbers. Oops. Actually, I just put some numbers. It should have done that. How do you call it? Oh. You actually have to call it like this. Call it as structure, some numbers. There you go. And that's how you call it, and it brings it up. So structure dot some numbers. Now this of course has a different usefulness. First of all, you can name things what they are and then keep track of them and then call them later and not get confused in your program as to what you're calling. If you have to call by index, you have to remember which index goes with which cell. If you're calling by a structure, then the structures are named and you don't necessarily have to remember as much. You know that some numbers is related to numbers, so on and so forth. So this is a higher level of programming, but a more useful level of programming. But as far as everything else that you can do with this, it's pretty much the same as the cell arrays. It does look different when you look over here as well, if you open up the structure, then let's see if I, that's not what I want to do. If I open up the structure, then it stores each one of them under its own array, essentially, under its own tab. And there's another way to do it. If I do structure, if I type in structure down here, it displays it differently down here under each one of its names, under each one of its whatever they call those things, structures. Anyway, so different ways to do things. The last thing that we have here is section 11.12, page 430, is an array of tables. Okay, I've never seen anybody do this before, but you can do it. And in an array of tables, okay, so if you look on page 430, they're importing some data from an Excel file where essentially each row is a table of numbers, I think is what they're doing here. And what they want to do is for each row of data, they want to plot that data. So they're going to plot the data for each row, and each row has different things. It has dates, it has numbers, it has strings and other things like words and things. And so in order to sort all that out, you import the data, and then for each one of those imports, you can sort it out using the date time function like they do on page 431. You can also sort out the data and plot it, and then save those plots inside of your array, or have those plots print from your array rather. So in other words, if you're bringing in large lists of numbers, you can separate that list into tables, and then import each one of those tables separately, even though you're importing them all at a time. It puts them into an array, each row separately, so that you can keep the numbers separate. And that is extremely useful because dates, of course, when they're stored by computers, are an array of numbers themselves, right? And so are times. It's an array of numbers. So it's essentially the same thing as before, where you're importing arrays into cells and kind of storing them together so that you can know that this cell is a date. These are just more and more advanced uses of the cell array. The cell array covers all of this stuff really, and they don't really give us much detail into that because we're not expected to use that much. But anyway, this chapter is all about how you can use the cells or the arrays of MATLAB or the matrices of MATLAB in different ways, and just mix it up a little bit to use MATLAB's functionality with arrays to manipulate more than just numbers. You can now manipulate strings. You can now manipulate arrays of arrays in cells. You can manipulate all kinds of things in different ways using structures or using cell arrays or using the date time arrays or whatever you want. You have a lot more a lot more things that you can put into your programming this way as you go into things like your final project. So that takes us to the end of that chapter and at the end of today's lesson. Anybody have any questions they want to ask before we break for the day?
I've got nothing.
All right, well, then we will go ahead and stop this video for today. Enjoy your week. Homework is posted. And I am working through the homework, grading it, I promise. I really am. We'll see you later.
See you.